All right, I'm just keeping it going. Hope we get this recorded. You can probably see what time it is. It's 10:15. Our live class is starting in 45 minutes. I'm trying to get every minute I can. And we gotta enjoy some music, folks, right? I mean, if you're sitting here watching me do math in my living room, you can also watch me like jam out a little bit. Let's keep it going. Okay, so let's talk about now real gases. It was only like about a 30-minute lecture on this idea of ideal gases. And I do kind of expect that was mostly review, but if not, if there was some stuff that was unfamiliar, reach out to me. Let's talk to make sure that you're feeling good about your ideal gas stuff. Okay. So I expect this coming up, this part of this material is going to be fairly new for you. Okay, so number one, real gases interact. Okay. We also know, I forgot to put a point number two here. We also know real, whoa, let's try that again. We also know real gases have volume. Okay, but I'm not going to focus on that as much for right now. This is what we want to talk about. Okay, so real gases interact, and there's two types of interactions: attraction or repulsion. So in that last lecture, I was talking about attraction. Attraction through hydrogen bonding or through London dispersion forces. And the effect that attraction has on a gas is that it can actually make it compress when, of course, the container is free to move, right? In a rigid container, you'll just see a decrease in pressure. But if the container was not rigid, you would actually see some compression, some change in volume, okay? Conversely, repulsion, so if the interaction is not favorable, so meaning like maybe two positive charges repelling each other, that would result in expansion. Of course, if it was a non-rigid container. If it was a rigid container, it would just result in an increase in pressure. Okay? We want to keep this in mind. Attraction equals compression, repulsion equals expansion. And there is, as it turns out, a sweet spot. Okay? If I draw a potential energy potential energy diagram, and we're going to get used to seeing these types of diagrams. So I'm just going to say potential energy on this axis. And then this axis, I'm just going to call separation. And by separation, what I mean is like the distance between molecules or atoms. Okay? Our potential energy is going to look something like this. Okay? So there is going to be this region where the separation is small, right? So on this side of the scale, the separation is quite small. So that would give us repulsion. So that would give us what I called an unfavorable potential energy, so a large potential energy. As we'll explore in this class later on, we'll see that potential energy really wants to be minimized. If we can minimize our potential energy, that is beneficial. That's a favorable interaction. Okay? But now, if they're too far separated, right, there may be somewhere out here, okay, the potential energy is going to want to drive them to actually compress, okay, to attract each other, okay? So that side of the curve is attraction. And right here, this represents the sweet spot or their equilibrium position, if you will, the function of state. This is where the state would exist at that minimum, okay? And so we use the compression factor Z as a means of kind of telling us where are we at in this range, okay? So I'll define the compression factor Z as Vm, remember that's molar volume, intensive property, over Vm standard, okay? And so we remember that Vm equals V over N, And of course, Vm standard, or even Vm ideal, we know is with 4 sig figs 22.42 liter per mole. Okay? And so there's a couple different ways that we could calculate what the compression factor is, right? We could say, well, if we know that V over N equals RT over P, this is just doing some algebra with the ideal gas law, okay? That, if I plug in STP conditions, so I'll put a standard and a standard, then I get this Vm standard, okay? So that's right, 273 and 1 ATM, that I would get that 22.42 liter per mole. So now that means I can say, well, then the Z, because Z is Vm over Vm naught, then that's going to be P, and I'm not going to put standard, this is just whatever the pressure is, times Vm divided by RT. Okay? So, right, keep in mind, now this P and this T are just whatever the observed pressure and temperature are. Okay? And, wait, did I say that? No, I said that wrong. Excuse me. Okay. Because, yes. Excuse me, those have to be the standard. Apologies. Now, this molar volume right here is going to be the molar volume as a result of whatever the pressure and temperature is. Okay, right? So go back to this. This Vm will be nRT over P. This Vm standard will also be nRT over P. But one is at standard conditions and one is at whatever the other conditions are. Okay? And so another way to write that would be P Vm equals Z RT. Okay? So now we have a few things to consider, right? Because if you think about this, right, if Z is equal to 1, then we just have our perfect ideal gas. Okay? And so as it turns out, this is typically in a low pressure regime. Ideal gas is typically low pressure. Okay? When Z is greater than 1, let's think about this for a minute. Okay? So this means when Z is greater than 1, this molar volume, this observed molar volume, is greater than the 22.42 liter per mole. And that would mean expansion has to be going on. Okay, so we'll say that would be expansion. And so the result of that could be from repulsive forces dominating. And that's going to be from high pressure, right? Because under high pressure, we'd be forcing all these molecules to get together. And perhaps they don't like that. We're forcing them to get too crammed together. So they're going to want to separate. And when Z is less than 1, okay, this molar volume right here has to be less than our 22.42 liter a mole. And so that means compression is going on. Okay. And I'm going to call this moderate pressure, kind of somewhere in the middle. And so here attractive forces are dominating. Okay. Oh my gosh, I'm sorry, you guys. I'm getting my nomenclature wrong. You're probably all freaking out like, at 2 minutes, I don't know what we're talking about. So let me just make sure we're still on the right algebra here, right? Standard, right? So to go from here to here, all I did was just a little bit of algebra, right? Okay, just to make sure that we're on the same track. And keep in mind, right, I didn't put the standard here on this molar volume or on this molar volume because that indicates whatever the observed molar volume is, okay? So again, when Z is equal to 1, when the compression factor is 1, that's an ideal gas. When Z is greater than 1, there are repulsive forces dominating, so the particles are like being forced to get close together, so that's high pressure. And so when Z is less than 1, there's attractive forces dominating, right? It's influencing those molecules to occupy a smaller volume than the 22.42. And as it turns out, that's like moderate pressure. So we'll put more quantitative qualifiers on that as we go, okay? So now we get to the virial equation of state, so another type of equation of state. And the virial equation of state is really useful because we can use this idea of compression factor to assist us in the virial equation of state, okay? So I'm going to go ahead and write it down. It goes as P Vm equals to molar volume RT. And then I'm going to write this up in the corner, right, just so you remember, P standard Vm equals Z RT. So this was another way of writing the compression factor. So you can see where we're going with this already, right? And I'm going to drop the standard notations here because we are drafting up a new equation of state that's just going to describe whatever the state of this equation is, okay? So PVM equals RT, so you can kind of start to see some similarities, okay? And now times the quantity, 1 plus capital B divided by Vm plus capital C divided by Vm squared plus so on and so forth. So if we wanted another term, it would be D divided by Vm cubed, okay? And so this number 1 here, this is what we call the, let's change colors. This is the first virial coefficient, okay? This B term is the second, C is the third. I'm going to actually clear up some room for myself here. Ooh, oh, that's good. Okay. Yes, second. And of course, if we wanted a fourth or fifth or sixth or seventh, right, this is an expansion of powers, then we recognize it would be like 1 over Vm cubed, and D would be the fourth coefficient. The fifth coefficient would be E over Vm to the fourth power, if we needed that. But of course, in these expansions of powers, we only put as many of those terms as we need based on the precision we're trying to achieve. Okay? So let's rearrange this a little bit. And if I divide this out, if I say PVM divided by RT, that's going to be 1 plus B over Vm plus C over Vm squared, et cetera, et cetera, et cetera. And now if you compare these two expressions, okay, and I rearrange this, then I recognize all of this is another way of writing the compression factor Z. Okay, so let's write that out. Okay, so now I can say Z equals 1 plus, and I'm going to do something different here with this Vm. I'm going to remind you now that this Vm, the observed molar volume, is just RT over P without these standard notations, okay? We're going to make sure really try not to confuse us with all this differing notation, okay? So this molar volume, right, this is our observed molar volume at whatever the pressure and temperature are, okay? So now instead of writing this as 1 plus B over Vm, I can actually write this as 1 plus P times B divided by RT. So I got that because this is 1 over Vm. 1 over Vm is P over RT, so P over RT times B. Okay? And then, of course, the next term is going to be plus P squared C over RT squared. Okay? And now what becomes useful with this allows me to think about Z as a function of P and T. Of course, here I have Z as a function of Vm, right? But this is the whole idea of these equations of state, right? Being able to write these in terms of whatever states, whatever variables rather we want, okay? And so if we do some analysis on this, okay, if we were to say, for example, dz by dp, so what is the dependence of the compression factor on pressure, dz by dp, right? Then we would get, whatever derivative this is, right? So we recognize all of these are constants. So I'm just going to write this as b prime because we recognize here that the pressure would drop out. So then I would just have b over rt. I'm just going to write that as b prime, like call it a new constant. And it's a new constant without a pressure dependence. And then now this term, right, is going to be 2p c prime, and I'm just going to also write c prime because I recognize that c over rt squared will be another constant if we're just interested in dz dp at constant t, okay? And then of course, more and more terms. And as it turns out, when there's a special case, when dz dp equals 0, so when all these terms converge to 0, we have an ideal gas, okay? Or rather, when dz/dp approaches 0, when it becomes very close to 0, that's the description of an ideal gas, which makes sense if you think about it, right? If the compression factor has no bearing on the pressure, that's saying there's no interactions, right? There's no attraction or repulsion if dz/dp equals 0, or if it's very, very close to 0. Okay? And so I'll give you an example of this. I'll draw a graph right here, assuming I have enough room. And I'm going to draw this graph. This is going to look a little goofy, but here I've got z on this axis and p on this axis. And this line that I'm drawing here is not the 0 line, rather it's the z equals 1 line. Just go with me here. This is, z equals 1, okay, which we know is the ideal line, right? And there are 3 temperatures I'm going to highlight. There's one where the curve, let me make a different color here, okay? So 3 different temperatures. At a high temperature, compression factor is going to increase like this. So I'll say, I'll just write high T, okay? At a low temperature, and also consequently low pressure, Z will be less than 1. Okay, we'll write low T. Right? Keep in mind, right, this region right here, this is the low pressure region. This whole curve describes a low temperature. So this is if I'm just doing Z as a function of P and specifying, some constant temperature. Right? So under low pressure, the temperature is also sufficiently low enough here that it makes attraction possible, right? This is the region of Z less than 1, okay? Z less than 1 here, Z greater than 1 here. And then finally, there's a very special temperature. It's called the Boyle temperature. That's not like the boiling temperature, rather it's called the Boyle temperature, named for Boyle himself. And as it turns out, the Boyle temperature is a special case. I'm going to keep going on this with more slides here. I know I'm getting a little full on the slide. So the Boyle temperature is specifically when this term B equals 0. Okay? Because when this term B equals 0, obviously this term drops out. So there's still this 2pc dependence, okay? And that's why what happens at the Boyle temperature, it's this kind of temperature where over, a low to modest pressure range, the Z stays as 1, but eventually as the pressure starts getting high enough, this term will dominate and take off, and the gas is no longer ideal, okay? So let's keep going, okay? So here is a summary of all that. So this is obviously a much better looking graph than what I just drew. The boil temp, some higher temp and some lower temp. And what I want you to keep in mind, this compression factor, if this line is like 1.00, under like most modest temperature and pressure ranges, this is not a big difference in this compression factor. So this line right here might be like 0.99 and 0.98 and 1.01 and 1.02, right? We're hardly ever going to see compression factors that are like 1.5 or 2.0, right? We're not going to compress a gas like by a factor of 2. We might compress a gas by like 1% or 2%, okay? Or we might expand that gas by 1% or 2%. So, so it's not reasonable to see these compression factors go up by these giant factors, okay? And so what's on my next slide? What do I want to say next? Okay, so and then what I want to say next about this, I'm going to give you some definitions of B and C. So let's go ahead and write the virial equation of state again. PVM equals RT. Let's start that again here. Okay. PVM equals RT, 1 plus, and I'm just going to write this in terms of VM, but we recognize we can do coordinate transformation and make this a function of P and T if we want. Okay, C over VM squared, etc. Okay, so what we're going to do in the coming slides is show that B, this virial coefficient B, is equal to little b minus A over RT. And yes, those A and B's are the van der Waals coefficients. Let's change the color. Okay, so these are our van der Waals coefficients. Okay, so we can calculate these B terms. So these are specific for a gas, right? Because it depends on what type of intermolecular forces they have available. And the C term up here is equal to B squared. And yes, that's the same B in the van der Waals coefficient. Okay, and so let's see here. What else can I say about this? So you kind of saw typical values for A and B from that previous slide, if you recall. So B is always about 10 to the minus 2 liter per mole, and A is, in the vicinity between 1 and 10 atm liter squared per mole squared. And so what that means is this A term really can dominate. Okay, so for example, we notice here that this C, right, in this equation is B squared. And if B is 10 to the minus 2, and then I square it, that makes that term pretty small. So that's why this C term doesn't really start taking effect until you get to fairly large pressures, right? So you can see at this boil temperature, in this region right here, this is really corresponding to B equal to 0, right? So, as you might guess, if we know B equals 0 for an ideal gas, and that corresponds to the boil temperature, what's the equation for the boil temperature? Okay, pause the video right here, just see if you can think about it for a second. I'm going to move on and write that up. Okay, so at the boil temperature, this B equals 0. I'm gonna show in the next lecture video, because it's kind of a lengthy derivation. Yay, third video, lengthy derivations. I know you guys love it. B minus A over RT. Okay, so now I can do some algebra and solve for T. I would encourage you to do that. Okay, pause the video and do that. Otherwise, you can watch me do some algebra and get the answer, okay? So that's A over RT equals B, and then flip the position of T. And so now that's T is going to equal A over BR. So again, this is another kind of cool thing in PChem, right? We, like all of these fundamental constants, A, B, and R, we combine them and we get to something specific. Very cool stuff, okay? And so I'm going to have you in the next exercise calculate this stuff, and I'm also going to do a derivation. But I think I'm going to save that for the next video, which will be a short video, and it'll be the last one for this week. Okay, folks, I'll see you later.